Okay, so first thing we're going to talk about is seeing if we can find some of the areas here. Which one would you like to focus on?
Let's focus on this biggest one here.
Which one?
This here.
In the middle?
Yeah.
Oh, okay.
Isn't that infinity?
Well, let's go back to the beginning. Where's that area now?
Well, it's kind of cut into two halves here.
Okay. And what do you think is going to happen? Because we are actually just kind of zoomed in a little bit on this graph. You can see that where I draw the graph here, which is this function called contour plot. Mm-hmm. I go only from -5 to 5 and -1 to 9 on the y-axis. So x goes -5 to 5. See that? Mm-hmm. Y goes from -1 to 9. Note, see they're both 10?
Yeah.
So I get a nice little undistorted square here, sort of anyway. And that area is in here. But what if I didn't? What if I went from x goes from -infinity to positive infinity? What would that area look like?
Well, it would be infinite.
Yeah.
So,
Wouldn't it just sort of look like a line going up at 0? Like, if you were completely zoomed out on this at infinity, wouldn't it just look like a line going up at 0? Since it would be so close to 0.
What would be so close to 0?
Like, this parabola is so close to 0 if you're zoomed at infinity.
Well, but on every point, like at x equals 10, it's going to be up at 100 on the y-axis, but it is still going to be 10 away from the axis. And at x equals 100, it'll be 100 away from the axis.
So it may be hard to see that if you're at infinity.
It might be, but even when x is getting near infinity, it's still part of the graph is moving away. It'd be interesting to see what it would look like. Maybe it would look really skinny. Let's go from -20 to 20. So
It's x-axis?
that's the x-axis.
and maybe from y to -1 to minus.
So I'm going to go from -1 to 39 to make it a square.
Yep. Got really
It does get skinnier.
So it does seem like it is getting skinnier if I keep the distance on the x and the distance on the y the same. But what if I go up to 400?
like -1 to 399.
Well, I'll go up to 400 so it's on there. But now it's starting to look fat again, but the problem is
You
my
haven't changed.
scale is different.
Yeah, you're zoomed in on the y-axis differently than you're on the x-axis.
Yeah, so that's actually an interesting observation. Maybe when you do zoom out, if you keep the x-axis and y-axis zooms the same, maybe it would start looking skinnier and skinnier.
Maybe.
It's good intuition.
So.
But let's go back to the area. So do you see that area you were looking at?
Yeah, it was. Well, I think some of my areas were only created when we rotated it.
Yeah, so let's go back to rotating 30
So
degrees.
like these areas were only here when we rotated it.
Yeah, so those are definitely, or well, I shouldn't say definitely, they look like they're finite.
Yeah.
Yeah? So how would we study those areas? What could we do?
Well, we could like find the area of one of these boxes and then kind of subtract the area away.
Yeah,
Well, that's gotta be kind of hard.
Maybe, yeah. But although maybe I can zoom in on them and we'll see. -1 to 1 and maybe looks like that one goes up to.
A little less than 4.
Well, actually, you know what? Let me do -1 to 1, -1 to 1, and see what we get.
Something went error.
That's because I didn't put the 1 in.
There.
There we go. Well, there's one of those
That was
areas.
the little
anyway.
one.
Yeah. Wow, we really zoomed in.
Yeah, we did. We really zoomed in.
So I was thinking to find those areas, if we could find the length of the blue line that is in the first quadrant.
Uh-huh.
We could maybe bend that into a circle and find the area of that.
That's it. Actually, that's kind of a cool idea. Y goes up to 2, even though we're going to be a little distorted now. Y goes up to 3. I'm getting there. You can
It
start.
gets skinnier.
Well, we're distorting because we have different things on the x and y axis. But so you would take the length of this line or curve, if we could find that length, and bend it into a circle and see how much area was inside the circle.
Yeah.
Okay, yeah, that's an interesting idea.
But
Do you see any other ideas you might have to calculate the area of these shapes bounded by curves? It's a tricky question, actually. People have struggled with how to do this. So this is a neat question to try to think about. What else could you do to find this area?
Well, what if you duplicated it and got an oval-like shape?
Oh, you mean flipped it, like made one going the other way, going down, so you had an oval on the inside?
Yeah, so you had like an oval shape.
Okay. Yeah, then we would have twice the area.
We'd have like would that be an ellipse?
Maybe. And then we could just find the area of the ellipse.
And then divided by 2.
And then divided by 2? Yeah, maybe. Though I'm not sure we know how to find the area of ellipses.
Yeah, circles maybe, but...
Circles, maybe. Yeah, so your circle idea is not bad. Well, let me give you this idea. What shape does this, let's say this one up here, kind of look like?
Looks sort of like an egg.
Okay, how about a shape that you know how to find the area of? What does it sort of look like?
Triangle, actually.
It does kind of look like a triangle.
Because it looks sort of like a triangle, but this edge is rounded. Like if you had a triangle going like that.
Yeah, so what if we approximated it by a triangle? And then found the area of the triangle? That might give us an approximation.
Yeah.
Well, maybe.
Yeah. That's one way to do it. Another way, you ready for this?
Yeah.
Is we also know how to find the area of little rectangles.
Oh yeah, we could break it up into tiny rectangles and find the area of them.
Yeah, break it up into tiny rectangles kind of going up like that and then find the area. That's a great question. That's a really good question. Okay, ready for the next one?
Yeah.